Good afternoon, everyone. I'm back. So imagine that you're walking across a room full of carpet, and then you go over there to shake someone's hand. You shake their hand, and you feel a shock. The moment that you felt that shock, it's because you felt there was a little particle, and it was called Q. Now what's Q? Q is just charge. That's all it is. Q is charge. I'm going to put it right here. Now, today I'm going to explain to you why this little particle matters, and then why this little particle matters, and how I can relate this to something that you guys see in your everyday lives. So I'm going to start with this. First, we're going to analyze this one little particle. First, you really can't say much. It's just there by itself. So that's why I'm going to bring in another particle. But this time, I'm going to name it negative Q. Right? Now, I'm pretty sure you guys have heard this term before. It's called opposites attract. So clearly, these two guys, they're going to come together. But the question is, where's the force coming from? How is this happening? Alright, so the force is being caused by this. So the force is, I'm going to give the equation for the force. F is equal to K, Q1, Q2, over R squared. R is just the distance between the two. So it can be a mile, 2 miles, a meter, 1 centimeter, it can be anything. Q1 is just the first test charge, and Q2 can be the second one. And they can be vice versa. K is just a constant. So I'm going to label what I mean first. I'm going to do F is just force. And our force is just a push or pull. And K is, it's just a number. And it's just this. 9 times 10 to the power of 9. That's what K is. Now, so this really isn't telling me what the force is causing. Until one day, physicist Michael Faraday, he said, hey look, what's this? We're going to take only one charge. And what one charge is doing, the way it's behaving, it's causing an electric field. Now what is an electric field? An electric field is a region around a charged particle or object within which a force would be exerted on other charged particles or objects. Now, so this equation right here is just my electric field. So here we go. E is equal to Q. I just need Q because this is only 1 over R squared. And E, I'm going to write it over here, what it is, what it means, and it means electric field. And electric field for short means E field, is E field. So you guys may hear me say E field a lot, but it's the same thing. Okay. So electric field is what's causing these attraction. That's the mysterious force between it. And no, it wasn't Star Wars this whole time. And now that we know about this, we can move on to another concept. So this is only for a point particle. And a point particle means very, very small. So what if we bring something that's very big, like a charged plate? So that's why I'm gonna get a charged plate. It's a metal plate, it's just square. And I'm gonna charge it. It's gonna be all over the place. And it can be anywhere, doesn't matter. And this plate is gonna have a charge density of rho. Now, charge density means it's the amount of charge per unit area. So I can get this little paper, and I can sprinkle a charge here, a little bit more right here, and maybe like nothing right here, maybe right here. But yeah, that's what rho is. So it's just to generalize it. That's why I'm using rho in this case. Now, what rho can do is, so we know this, and we need to know the change in area. The reason why I'm using delta A, it means change in area. And the area, it's changing as I go along, because it's just to generalize this idea. And now, we're looking for charge. That's what I want, to find my E field of this plate. And so, I'm going to use charge of Q is equal to rho times dA, delta A. So this means the change in charge as I go along is equal to my charge density times the change in area. So, now using calculus, we can derive a formula, but I'm not going to use it. I'm going to skip all over the calculus, and I'm going to get you guys to an equation. It's equal to rho times epsilon 0. And now what epsilon 0, it's just 1 over 4 pi k. And we know what k is. K is just 9 times 10 to the negative 9 times 10 to the 9. And 4 pi is just 4 times 3.141, we can go on and on. So, we know all that. So we know this, and now we can move on to another concept in negative. And we can move on to something called, so we're going to have another plate, just like that one. I'm going to throw in another one. Now, you guys are probably thinking, oh my gosh, this looks insane. But no, trust me, I'm here to guide you guys. So I'm going to get, so the plate is producing an electric field, right? It's producing an electric field, and then both of the plates, they have an area, and they both have a charge density, right? And then we just found out, using calculus, the imaginary calculus, we just skipped through it, that the electric field of one plate is equal to sigma times epsilon 0. Now that's for one plate. Now, what I want to take you guys, also I also want to mention, is that they're both separated by a distance x. Okay? Now, we're going to bring in another variable to this. It's called capacitance. Now capacitance, what it means is, it's the measure of the ability for a device to store energy by using a separated charge or an electric field. So, and I'm going to write the equation for the capacitance. It's C is equal to Q over V. Now Q is just the amount of charge, and V is voltage. Voltage, I'm going to tell you right now how it relates to this. And so, I'm going to bring in another equation using voltage and electric field. Electric field is equal to the voltage over X. So, what this means is that I'm going to start right here, and as I go down, my voltage is going to decrease. So if I start right next to the plate, that's when my voltage is maximum. And as I go along, as my X increases, that means my voltage is going down. So I'm going to solve for voltage, just using simple algebra. I'm just going to multiply the X over. I'm going to do this. E times X is equal to V, right? Now, we know what E is of one plate. This guy right here. So I'm going to bring it down here. So over epsilon 0 times X is equal to V. Now, Q. How are we going to get Q? Well, I also told you it's right there. Q is equal to sigma times A. We know our area, and we know that there's a charge density. So I'm going to write it right here, right next to it. Q is equal to the charge density times A. So we know about this. So I'm just going to plug these guys in, and I'm going to relate the electric field and the capacitance. So I'm going to label this as star, this is star, and I'm going to move, let's call this triangle. I'm going to move it to triangle. That's it. I'm just plugging my equations that I derived, and I'm going to plug them in. So I'm going to do this. So it's going to come out right here. So C is equal to Q, what we have here. I'm going to put it up right here on top. Times A over my voltage. My voltage is down here. I'm going to get this. Take it here, over epsilon 0 times X. Now, check this out. My charge densities go away. So what does this mean? When my charge density goes away, I don't care what my charge density is. I can have a bunch of charge here, and like little charge here, or I can have no charge here, and just have all my charge here. That's what it means when I cancel my charge density. So, I'm going to clean this up, and then it's just capacitance is equal to the area over X times epsilon 0. And that is that's one of the formulas to calculate capacitance. And now I'm gonna apply a capacitor to something that you guys see, and it's called an electrical circuit. So I'm gonna give a general electrical circuit. I'm gonna have a power source here. Now the power source here, the purpose of it is just to produce charge. And it's going to produce a current, and I'm going to go more into detail right now. And it's going to have a resistor, and it's going to have a capacitor. Now for those of you that have taken Physics 2BG or Physics 4B, you guys can see that this is a RC circuit. Now this is a resistance, I'm going to label this as R, and this is C. So what does a resistor do? A resistor, it takes away energy that you cannot get back. C, it's just going to charge up. And this is my power source. I'm going to label it as epsilon. Now, epsilon, this can be anything. It can be V, it can be, but for now I'm just using epsilon. So, this is what's going to happen. I'm going to start this circuit up. It's going to go down, and then this is the current. Now, what a current is how fast the charge is moving through the wires. Right? So it's going to go down. It's going to go through a resistor. Now, with a resistor, it can be a light bulb, it can be a fan. But for now, if you guys want it to be a light bulb, I said light bulb is the best, right? Now, the moment it gets here, it acts differently. This is what happens. When it comes here, the capacitor begins to charge, right? So once it starts charging, like the moment it's fully charged, then the whole current, it stops. Current just says, because the reason why it stops is because the force, they're pushing, the force just says, hey, wait, stop, just stop. They're like, okay, we're full. They're just like, not allowing anymore. They hit max capacity, we're done, they're full. So once it hits there, so it's pretty much the current, it doesn't flow. Now, you guys may think, oh, this is like similar to my phone, my battery in my phone. No, this happens in like, not even in a millisecond, faster than a blink of an eye, like that. This guy is going to charge really quick. Well, when it discharges, this is the best way for me to explain it. If you guys have seen like that, like go to the hospital movies, they have those like defibrillator units, like try to revive someone, and it gets like dramatic music. You guys seen those? Right? So, this is the way how when it discharges. So the capacitor, it needs a quick spike of energy, like really fast. So the moment it charges up, like clear, bang, like really quick, just a jolt. It's going to discharge really fast. Now, look at your guys' phones. I want you guys don't have to take them out. Look at your guys' phones. The flash inside there, that's a capacitor working. That's the flash is coming out from a capacitor. That's what's going to come out. So the energy from a capacitor, you're going to press the button you're going to press a button on your phone, and then it's going to produce a flash on your camera. And the moment it does that, like it's because the capacitor is going to discharge, it's going to produce a quick spike. So now that I explained how all this derived, I derived from just one simple point particle. I went all the way down to electrical fields, all the way down to capacitors, and I came back to and I plugged in my capacitor into a circuit, and all of this, just remember, it all started just with one simple point particle named Q.